For our first proof by induction, we're going to look at a formula you may have seen before. This says that the sum of the first n positive integers is equal to this formula. And the first thing I want you to notice is that this is a statement about a formula whose values can only be integers and that have a fixed starting point. Those are the things that should immediately make you think, okay, maybe this mathematical induction technique is going to be effective here. All right, and down here at the bottom, just for reference, I've written out the two steps, the basis step and the inductive step that we need to go through to prove that this is true. Okay, so the first thing I want to do is I want to be clear about what P of A is. All right, P of N, actually, let's use N for P here, because that's the variable that's used up here in the formula. This formula here, this is P of N. That is our predicate, right? It says that the left-hand sum is equal to the right-hand formula. All right, so what's the basis step? Well, to show the basis step, I have to show that the formula here works for the minimum value. I have to show that it works for 1. All right, so if n equals 1, then what's the formula say? If I put 1 into the formula, I get 1 times 1 plus 1 divided by 2, which is 1. Which would be the left-hand side, right? If n is equal to 1, then there's none of these numbers here, right? And it's just that single number. Okay, good. That's what you needed to show for step 1, and that is all of step 1, right? And this is, if that seemed a little trivial, that's actually kind of normal. It's not unusual for proving the basis step to be relatively straightforward, certainly compared to the rest of the proof. All right, so what do we need to show now? We need to show that if P of n is true, then P of n plus 1 is true. Well, we know what P of n is. I defined it up here, right? P of n says 1 plus 2 plus so on out to n equals that formula, n times n plus 1 divided by 2. And I'm actually going to rewrite this. I'm going to write that sum using our sigma notation. And so this is the sum I equals 1 to n of I. All right, so what is P of n plus 1? All right, well, if P of n was the sum from I equals 1 to n, then P of n plus 1 will be the sum I equals 1 to n plus 1. And what I need to show is that that equals this formula, right? So if I put n plus 1 in there, it becomes n plus 1. And the second factor, that's n plus 1, which is n plus 2 over 2. All right, so I want to be clear now, right? This is what we're trying to show. Okay, so how can we do this? Well, let's start with what we're being asked about, right? We're being asked about the sum I equals 1 to n plus 1 of I. Now, you remember, if you think back to our earlier discussion of sequences, remember we saw a method where we could kind of peel off the first or the last term of a series and write it separately? Well, that's what I'm going to do here, right? I'm going to rewrite this, the sum I equals 1 to n of I plus that nth term. All right, well, what is the nth term? Well, if I put n plus 1 in there for I, it's just n plus 1. Okay, good. But now look, I know what this sum from I equals 1 to n is. That is my inductive hypothesis, right? I'm assuming that the formula works for n. So I'm going to put n times n plus 1 over 2 here. Still plus n plus 1. Now, great. See, it's a very algebraic sort of proof. Now I want to add these two expressions together. And to do that, I need a common denominator, right? So I'm going to put the n plus 1 over 2, and that's going to make this n times n plus 1 plus 2 times n plus 1 all over 2. Excellent. Now, starting to come together. Notice that both of those parts of the numerator have an n plus 1. Let's factor that out. Right? If I factor that out, this becomes n plus 1 times n plus 2 over 2. And look at that. That is exactly what I needed to show. Right? And that's the end. Right? We've shown that if this is true, then this must be true. Right? And that's the second step of our inductive proof. Okay, so let's take a step back here, right, and be clear about what we did. Okay, first, this part here, that is the basis step. Right, that was step number 1 here. Everything else that we did, everything from here down, this was the inductive step. Right? Once we had proven both of those two things by mathematical induction, the original theorem must be true. So I've got a second example here, and it's another kind of algebraic example. We're going to prove this formula that says the sum of the first n powers of 2 is equal to that formula over there on the right-hand side, 2 to the n plus 1 minus 1. So again, you see we've got very similar things going on here. We're talking about something that only works for integers. We have a well-defined starting point, right? This starts at n equals 0. And then we have a formula to work with. So first, what is our P? What is our predicate here? Right? Our predicate is this formula. Right, so what do I need to do first? Right, my basis step, I need to prove that this is true for n equals 0, because that's the lowest value for which we're saying this formula works. So I'm going to say if n equals 0, then the left side is 2 to the 0, which is 1, and the right side is 2 to the 0 plus 1 minus 1, which is 2 minus 1, which is also 1. Good. The formula works for our initial value. Now we got to do the inductive step. Okay, so remember what we do here, right? I'm going to assume P of n and show P of n plus 1. So what does P of n plus 1 look like? Right, the P of n plus 1 is the sum I equals 0 to n plus 1 of 2 to the I power is equal to 2, and I'm going to replace that n with n plus 1. Right, so the numerator becomes n plus 2. It's all still minus 1. And let me give P of n the same treatment over here. P of n is the sum I equals 0 to n of 2 to the I equals 2 to the n plus 1 minus 1. So I know this over here on the left. I'm assuming that's true, and I want to show this formula over here. So from here, I'm going to proceed really very similarly to what I did in the previous proof. Right, let's start by looking at the sum. Oops, didn't change the color back. The sum I equals 0 to n plus 1 of 2 to the I. And I'm going to do the same thing. I'm going to peel off that n plus 1 value. So this becomes the sum I equals 0 to n of 2 to the I plus the last value, which will be 2 to the n plus 1. All right, now here I'm going to use that inductive hypothesis. I'm going to replace that summation with the formula. So this becomes 2 to the m plus 1 minus 1 plus 2 to the m plus 1. Okay, now I've got these two 2 to the m plus 1s here. Remember, it's a kind of a messy expression, but if it was just x plus x, that would be 2x. So I'm going to do the same thing here. This is 2 times 2 to the m plus 1 minus 1. All right, now I'm home free. I'm going to apply my exponent rules. Exponent rules say I can add the exponents together. So that becomes 2 to the m plus 1, which is m plus 2. And that is what I was aiming for, right? That's what I needed to show. And we're done, right? That's the proof. Again, before I was about to go on, but before we go on, let's take a step back again, right? And look at what we did here. I've got the basis step here, and the basis step started at that smallest value that we needed to show the formula worked for. Basis, let me label it, right? Basis step. And then everything from there down, this down here, this is the inductive step. Once I'd done both of those things, then we were home free, right? And we had proven the theorem. Okay, so now that you've got several examples of really kind of algebraic proofs to work with. In the next lecture, we're going to continue kind of a similar vein, still kind of algebraic. We're going to look at some examples of how you can use mathematical induction to prove inequalities rather than equalities.